Hi, everyone. Just before I introduce Nestor, I want to say there's 2 spots available for dinner tonight with Nestor and then a group of us at the Central Mexican Kitchen, 6 p.m. So if anyone's interested in coming to dinner, then just come and see me after Nestor's talk. So I'm very pleased to introduce Dr. Néstor Espinoza. He is an assistant astronomer at the Space Telescope Science Institute in Baltimore, where he works on the detection and characterization of exoplanets. He did his undergrad and PhD at the Pontifical Catholic University of Chile. I'm not going to try and say it in Spanish because I don't speak any Spanish. After which he was awarded the Bernoulli Fellowship for a joint position between the Max Planck Institute and the University of Bern in Switzerland. Since 2019, he's been working in his current position at Space Telescope and is heavily involved with not one, but 2 different major NASA Space Telescope missions. So he's worked extensively with the TESS telescope that was launched back in 2018, searching for brand new exoplanets from warm giants as a co-PI of the WINE survey, and small rocky exoplanets as co-lead of a Carmenus TESS collaboration team. Nestor's also been key in providing support for the JWST mission, which we'll hear all about today, where he's been working on the characterization of transiting exoplanet atmospheres. He is part of the NIRISS instrument team, and NIRISS is a near-infrared imager and spectrograph, and one of 4 instruments on board JWST. His talk will go into much more detail, talking about JWST, its potential, impact, and exciting new results. So here at CU Boulder, we've been lucky enough to work with some of the early release science coming out of JWST, and this is how I first met Nestor. But Nestor is one of these people whose name I had read on papers a million times before I actually met him, because he's authored and co-authored over 100 publications. He's also developed a number of key Python and C tools for the community. I'm sure many of us have used them, such as JWST, which is a modeling tool for transiting and non-transiting exoplanets, and this tool itself has over 100 citations. So I'm very glad that he's here today, and I'm excited to hear all about the cool new science coming out of JWST. So please join me in welcoming Néstor Espinoza.
Thank you. Thanks for that great introduction. I'm very happy to be here. A ton of names that I've heard, meeting people here, it's been amazing. And I'm super excited to be sharing with you some of the very cool science that is happening with JWST, in particular with exoplanet science, which is going to be the focus of the talk today. So in terms of a little outline of what's going to happen today. So first, I'm going to start trying to share with you some of the promises of exoplanet science, because yes, we've made promises, and some of them we're actually accomplishing already. Then I'm going to go into observing exoplanet atmospheres. How do we actually get this information out from our beautiful telescopes? And in particular, I'm going to focus on JWST observations, the newest ones, some of which are actually unpublished yet. So I'm going to ask for some care on pictures. Of course, the recording is fine, but it's only for you folks. And then I'm going to go a little bit on the future of JWST and exoplanets. What can you expect in the near future, in the far future too? So first of all, the promises of exoplanets. We all made promises, right? Sometimes we don't just make them, but in this case, I think we're standing up to the challenge. So as of today, we know over 5,000 exoplanets. That's a huge number. It's a milestone that we arrived at just very recently. And from these planets, we have a sample now that we can start asking very big questions, like how planets are formed, what are they made of? Does it have my favorite element, like water? And I think the one that I'm most excited about, which is how do we fit into this picture? How do the solar system fits into this exoplanetary context? So how can we make that connection? I really like to start on this with the promise, one of these promises, on exoplanet atmospheres as tracers of planet formation. So a little toy model on how atmospheres are connected to planet formation. So these planets, they form around these protoplanetary disks, around the beautiful star that you have around. And then after some time passes, your disk cools a little bit, and then some materials have the chance to get together and start forming these planets, right? And in our solar system in particular, we see 2 kinds of planets mostly. So ones are these giant planets that we're lucky enough that they capture a ton of material, enough material such that they go in this runaway gas accretion. So your core, we're thinking about 10 Earth masses of material. Imagine this big rock that we're standing here 10 times. If you manage to get that during the planet formation process, then you go run away, you start accreting gas like crazy. And then that forms the giant planets that we all love and that we see on our own skies directly. And if you weren't lucky enough to form all this rocky material around you, you still have an atmosphere like us that you can breathe, for instance, here on Earth. And you have these outgas envelopes in particular. So typically the atmospheres that we see in the rocky planets, they come from this outgas material. One big question is, does that same process happen in other planets out there? That's a big question mark. I mean, we expect them to happen, but that's a big question too. So you have these two kinds of planets here. From the giant planets, I mean, you've studied their atmospheres, their envelopes. You can actually start studying, how this gas accretion formed, how solids are accreted too. So there's not only gas in these protoplanetary disks, there's a ton of solids too, like little rocks that you can accrete, and even planetesimal collisions. And for the small planets, you actually can study this secondary atmosphere, and that tells you information about the cores, about the mantles in which they formed, and if that material is the same out there or not. That's something that we're trying to explore. So the thing that I'm trying to build here with you is that to share with you that these two kinds of planets and all in between, there's some planets in between that I'm not going to touch here, that we see in the solar system, exploring those around other stars has a ton of information that we can use to compare ourselves against them. Now, in terms of observables, there's a ton of discussion that you can build around this, but I'm going to touch on two basic observables that actually build a ton of information on the same topics that I just mentioned. And this is related to metallicity and chemistry. So most of here people are like half, I guess, are astronomers, so you're fine with the metallicity concept. Of course, any of the metals that I'm going to refer to are like not hydrogen or helium, basically, which is, might sound a bit dumb, but it's a very good point of view to start with, especially in this cosmic context. So in terms of metallicity, you don't have to go far away to actually find diversity in planets. If you look actually at our own solar system, you start finding this diversity of metallicity. So what I'm showing here, this is a beautiful paper by Atreya and collaborators that it's focused on Saturn, but it gives this beautiful perspective on all the giant planets in the solar system. So here I'm plotting all the elements. Well, they are plotting all these elements that you can choose your favorite to follow. And then in the y-axis, you see how much of those elements are embedded in the envelopes of different giant planets. So if the planets just accreted the same material of the sun, this will fall at the 1 mark here. So any planets that fall at 1, they mean that they have more or less the same protosolar abundance, at least that they accreted, basically. So there's the solar composition. So if you assume that just accreted directly by their capture, they call it. So in the solar system, you already start seeing that that's not the case for the giant planets. So if you plot Jupiter, for instance, Jupiter, it's about 4 to 5 times enriched in all these metals here, except for this little depletion. And I can talk about that later if you want. But on average, that's where it stands. If you keep going with Saturn, which is a lower mass planet, you start getting even more enriched, like 10 times on average, more or less. And if you go to the Uranus and Neptune, the smallest ones of this sample that we're showing here in our solar system, they're like 100 times enriched in metals. Actually, that might sound a little bit counterintuitive when you're joining the field. We actually have predicted this. This actually matches predictions from core accretion, like how giant planets form. You expect this 1 over mass of the planet enrichment. That's expected. So that's good. So one of the big questions is, does this thing matches exoplanets or not? And we're starting to do that. We can extract metallicity from planets. The problem is that this is very hard to do. This is the same plot, but I'm plotting here planet mass versus metal enrichment. And the black points are the solar system planets, very tiny error bars. But then if you plot the exoplanets, it's like very large error bars. So this is very hard to do. So I want you to capture these numbers. So we're missing metallicities like by 2 to 3 orders of magnitude. That was the status of the field. And I'm little hint, that's going to change with JWST. There's another part of this equation in terms of exploring giant planets out there, in particular. It's doing this is hard for planets, and even for these giant planets. Still not talking of the small planets yet. I'm going to get that to the end of the talk. But there's another part of the picture which is related to the chemistry, the actual chemistry that's happening in these exoplanets. And this is a very beautiful plot that was originally put forward by Karin Oberg back in 2011. And what I'm showing here is the radius, so where you form, where the planets, different planets form, as a function of a measure that we're kind of obsessed with. If you ask like the planetary scientists even, and exoplanet people, they're obsessed with the C/O ratio, like the ratio of carbon to oxygen molecules in an envelope. The reason for that is that a ton of the chemistry is actually defined by that ratio. So if you increase that ratio, the chemistry is very different if you decrease it. And that's one reason for that. The second reason is that depending where you formed as a planet, the CO ratio that you're going to be able to accrete is different. And this has to do with the fact that when the planets are forming in these protoplanetary disks, there's different what we call ice lines at different locations. So there's different portions in your disk in which if you get far away from your star, eventually you start frozening certain materials. So what I'm plotting here is that if you have a protoplanetary disk, like similar to the one that we should have observed here in the solar system, at around 2 astronomical units, you should start seeing water to start condensing out. So if you move away, and if you're at 1.5, you see all water in vapor. If you move away from 2 AUs, then you start seeing water condense out. That's the water ice line. But there's other ice lines too, the CO2 in particular and the CO, which are the most important ones for the C/O ratio. Depending where you are, then oxygen and carbon starts locking up in solids and in gas differently. So Karin plotted this beautiful plot here in which she kind of tracked these lines and starts showing how, depending where you form, your CO ratio is going to be different. But there's also a trick here because I'm plotting 2 lines. One line follows the gas, the solid line, and the other line, this dashed line, follows the grains, like the solid material. So when you ask someone in the street, which one do you believe the planets follow? People in the street will be, well, if you're following gas giants, they're made of gas, right? So they should follow the gas. Actually, in 2017, we showed that that's not the case. Planets should actually follow the solids, not the gas material. The reason for this is that we see, out of the bulk composition of the planets, that most planets are heavily enriched in metals. And there's no way that planets can get all the metals that we observe in them through their bulk compositions through just gas. They have to be very enriched in solids. So solids actually define a ton of the envelope composition. And that's a prediction. So this is a prediction that we made back in 2017, that the CO ratio should follow this line. So we expect lower than stellar C/O ratios in general. So if you measure the CO ratio on the star, the planets on average should all have less than that C/O ratio. That's a prediction that we're trying to actually observe with JWST, for instance. So these 2 metrics, it's the ones that I want you to focus on your mind. CO ratios and metallicity are like the big observables that we're behind to follow on planets. Now, in terms of characterizing exoplanet atmosphere, how do we actually do this? So there's 2 kind of ways in which you can, well, there's many ways, but I'm going to focus on 2 main ones. And those depend on whether you can actually resolve the planets around the star or not. So if you're lucky enough that you can resolve a planet, then you get to beautiful pictures like this one. This is not JWST data. It's actually ground-based data of the H8799 planetary system, in which you can actually follow the little planets going around, and you can even take a little spectra out of there, et cetera, et cetera. So that's super nice, but that only works if you can actually resolve the planets. So this actually only works for very nearby systems, such that it's easy to separate the star from the planet, and for very, very bright planets. So they have to be typically very young. If you want to go to the rest of them, then you have to find indirect ways of measuring that. And in particular, transiting exoplanet systems are very good at this. You can extract a ton of information from the atmospheres of planets if your planets transit. I'm going to explain in a little bit why. And actually, this is going to be the focus of this talk. The reason why I like transiting exoplanets so much is that you can do both giant planets and small planets. Typically, at small separations that are better, but you can do large separations too if you want. There's another, it's like they're complementary fields, of course, because they explore different parts of the parameter space. But direct imaging typically focuses on young giant exoplanet systems. So this talk, it's going to focus only in the transiting because that's particularly my expertise. Nothing against the direct imaging folks. I love their work. It's amazing. So for transiting exoplanets, perhaps the most popular technique that we're using right now is one technique that it's called transit spectroscopy. And this was predicted back in the early 2000s by a bunch of people, in particular led by Sarah Seeger and Dimitar Saselov, in a beautiful paper that they wrote. That story goes that initially no one believed that that was going to be observed. But now we're actually, we do this routinely. This is like my day-to-day work is trying to extract this signal. And the idea here is that when the planet passes in front of the star, part of the starlight passes through the atmosphere itself. So some signatures on the atmosphere gets imprinted into that stellar light, and you can actually extract that information to learn about the atmosphere. In practice, though, what we do is that we measure the transit light curve. This is like when the planet passes in front, like so this is brightness in the y-axis and time in the x-axis. So what you do is that you measure the transit shape as a function of wavelength. And then whenever you observe that the transit depth is larger, that means that something is absorbing a ton of it in the atmosphere. And whenever it's smaller, then nothing is like it's passing through the atmosphere. So absorption signatures going the other way. So for the spectroscopists in the room, when you see something going up, just don't scream emission, right? That's actually absorption for us when you look at transit spectrum. When you look at these transit depths as a function of wave. We're going to go through a ton of them, so you'll get used to it through the talk. Now, this all sounds very beautiful in practice. And pretty easy, right? Just go observe a transit and measure the thing as a function of wavelength. That's it. Now, in practice, this is extremely hard to do. If you try to do this from the ground, you have to measure actually two atmospheres, the planet that you're trying to measure and the Earth's. And here I wanted to highlight the work of Natalie Allen. She's one of the grad students which I'm working with back in Baltimore. And she wrote this beautiful paper on using a 6.5 meter telescope, so like very similar size as JWST, to do this from the ground. And this is the raw data that you get, like these red points. It's very bad. But we have pretty good models, and we can actually recover the signal because we have some comparison stars typically that we can use to correct atmospheric distortions. Because most of what you're seeing here is atmospheric distortions. There's a ton of the instruments that do not behave well and so on. But then you can detrend that. You can correct for that. And you can get transit spectra, actually. This is a particular transit spectrum from the ground in which we perform a tentative detection of water, like this little bump here. That's water. But it is very challenging to do. Like, we took like a year to reduce this data, because it's very hard. And I've dedicated like half of my career in trying to make this work. So it's a ton of work. So you might say, like, well, let's go to space, right? You don't have an atmosphere there. Well, even if you go to space, you have trouble. Here's a beautiful work by Jonathan Frame in 2013, in which you're seeing the transit light curve of an exoplanet through the lens of HST, the Hubble Space Telescope. And you actually see some system. It's not this beautiful like textbook light curve here. You have some features going around. And you have even some gaps, because HST has to pass behind the Earth, right? So you get blocked by your own Earth. The Earth photobombs your transit, like the worst. Like if you would delete the Earth, that would be great. But even if you deleted it, you have this ramp going up here. That's the detector, playing tricks on you. So it's pretty tough to do it even if you go to space. You could tell me, like, well, maybe it's just the HST detectors. No, if you go to other detectors like Spitzer here, beautiful instrument too, you also get like very complicated light curves to work with. So this is super tough. Now, this is the preamble to JWST. And the thing is that now with JWST, this was hard. Now this is easy to do. And like any of you can actually get a transit light curve right out of the box with JWST. That's one of the messages that I want to bring to you. And I'm going to show you some of that light curves. That brings me to the next part, which is observing exoplanet atmospheres with JWST. JWST, I call it the craziest space idea ever. I would have loved to be in that room when they pitched this idea to NASA, right? Let's build like a deformable space telescope that does everything in space alone. Like, that's a very crazy idea. Like, I would say no to that immediately. Like a 10 billion thing that has to like open up like a transformer in space, that's absolutely crazy. So the thing that I'm going to show here is like how it deploys, how it unfolds. All of this had to happen in space during 30 days. So this is just to give you some perspective, 6.5 meter diameter at 1.5 kilometers distance. Sorry, I'm using kilometers because that's like the right way in my mind. And in the way in which he was doing this, there was 300 single points of failure. If any of those failed, that's it, mission over. But this thing worked. Like, against all odds, the thing worked, and it worked beautifully. Like, look at those sheets like this, the sun shield. I mean, I cannot even do my own bed that tightly, right? And then this thing does it like automatically. It's amazing. So yes, everything worked pretty nicely. It was a beautiful JWST telescope launching on Christmas. That was one of those Christmases in which the scientists were more excited than their kids in Christmas, right? I was like jumping up and down that this thing was working. And 6 months later, on time, Space Telescope proud, on time, we delivered the first JWST images, right? So a beautiful instrument to work with. And I have to be very honest with you, I was extremely surprised on how well this worked right out of the box. I had the privilege of being in this early release observations team. So we were a team of like 30 people, scientists, illustrators, educators, people just wowing each other every day during commissioning while taking these observations. And the first time I saw these observations, we were just standing there for like a minute, just like staring, like no sound. It was amazing. In particular, my job in this team, I had a job in this team. I was just not there to watch. I had a job. And my job was actually to build the first exoplanet observations that I'm going to show you. If you haven't heard of JWST before, this beautiful space telescope that I just mentioned, here's some specs. It has 4 main instruments. There's actually a 5th FGS, which is the fine guidance sensor, that cover all the way from 0.6 to 28 microns. So it's like a choose your own story kind of telescope, right? You go and choose which wavelength you like, and then you observe with those wavelengths. But these are like wavelengths that have been basically unexplored at this level of resolution and detail as before. Some of them have been explored individually, but all together, it's just a dream come true. And as I'm going to show you, it's like a game changer in many ways. So OK, my job for the early release observations was to get an atmospheric spectrum of this exoplanet in less than 2 days. That's what they told me the first meeting that I went to with them. Like, OK, we need someone to like get this data and just put a spectrum out to the public in like 2 days. I realized that's absolutely crazy, right? Because I just told them, like, I'm just working with this grad student from the ground. I took like 1 year to reduce this data. Are you crazy that I'm going to do this in 2 days? And we trust that you can do it, and then just go and do it. Like, OK, let's do it. So WST-96b, it's an exoplanet that it's actually pretty far away. It's like 1,000 light years from Earth. It's a pretty puffy planet. It's at 30,000 Kelvin, so it's like not your vacation destination, right? So you don't want to go there. I mean, not judging, but you can do whatever you want with your life. It's like half Jupiter masses, but slightly larger than Jupiter, right? So it's like, that's why we call it puffy. And what I'm going to show you right now is one of the first transiting exoplanet light curves. So you remember the ones that I showed you before that were like all ratty and like not great? OK, the light curve that I'm going to show, it's basically the one that came out of the pipeline like right away. It's like this, right? This is the same face that I put together. I remember I triply checked that I was not running the pipeline reductions on my simulations, because I had simulations done for this. So I was like, no, this cannot be. Like, obviously, I'm wrong. And these are my simulations. So I checked from the servers. Like, this is the data right out of the top. It's amazing. It's beautiful. So what you're seeing, again, is just the transit as a function of wavelength. This is in Baltimore, Maryland time. So yes, we got the data very early. I was woken up very early in the morning, reducing this data to match the deadline. And we did it. Before showing you the transit spectrum that we observed for WST-96b, I want to show you what we had before. What was the state of the art before observing the spectrum with JWST? So the state of the art were these little points here. And you can see that they're like spread around. If you model them, you see a water feature here. But it's very tough to see with the eye. But once you put the JWST data on top of that, which, by the way, we were not allowed to do during the presentation of this thing, but I can do it now, because you've already seen it. This is the data that you see. So it's like, I'm going to go back and forth. This is just one transit with JWST. And you can see by eye the water features, like 1, 2, 3, 4. You can extract all kind of information from this. This is not just what they call eye candy, right? It has some information behind. So the amplitude of these features actually tells you something about the structure of the exoplanet. And actually, I ran some models too, and here's some of the retrievals that I made on that data. You can get like very beautiful pressure temperature profile out of that data. So yes, you can explore the atmospheric structure of the planet. And you remember that I made a big fuss about like CO ratios and metallicities? you get very precise, like 1 sigma errors. This is the blue end here. The errors that I was plotting on the plot in the very beginning were also 1 sigma errors, like between 0.5 dex, which is like, it's amazing that you can get just that with one observation of a very far away planet. This is a very faint planet. It's like not the best. It was the best that we could observe during this very narrow window for the early release observations. So this is the new frontier that we're playing. So the title of my talk was like New Frontiers in This is a new frontier. It's precision, abundances, and structure. And there's a paper now in the way led by grad student Michael Radica from the University of Montreal. It's like putting all this up in paper form with all this beautiful analysis together. I wanted to jump now to another planet. And this planet is very special to the exoplanet community, including Katrina and Zach Berta Thompson and all the folks that work on the early release observations. Because this planet was 39b. It's slightly cooler than was 96. Pretty similar in my agenda. In terms of mass and radius, it's also pretty similar, but it's much brighter, so you get much better precisions out of this. And as I was just mentioning, this was part of the early release science observations. I'm just going to do a little announcement here, basically. So there's a transiting exoplanet community early release science program for JWST. For those of you folks that don't know, what happened is that the director at Space Telescope decided that a bunch of the very first observations were going to happen by certain teams in the community that could build a program that could actually showcase the capabilities of JWST and also extract very cool science. And we got together. This was like over 100 people working on this proposal. And we all work hard, I can tell you that. We worked together on, this was the proposal that we built. So basically, we were going to do transmission spectroscopy, the technique that I just told you about. We were going to do emission spectroscopy too. So when the planet passes behind the star, you lose the flux from the planet, and that tells you about the day-side flux of the planet. And also, we were going to get a spectroscopic phase curve. So a whole orbit of a planet going around the star, so you can start seeing from the night side to the day side how it shows up to you. So 2 out of the 3 observations are happening, and this one is happening this week. So fingers crossed. Like this is happening at the end of the week. So we're very excited about that. So I'm going to be focusing on this transmission spectroscopy work, though. So who I just mentioned, the PI is Natalie Batala from the University of Santa Cruz. The co-PIs are Jacob Bean, Chicago, and Kevin Stevenson from APL in Baltimore. And the co-Is and collaborators are like over 100 exoplanet scientists. So it's like a big, big team effort. And again, why? Precision, best practices, exciting exoplanetary science. So we're building like notebooks, ePython notebooks, so you can like deal with the data yourself, repeat the signals that I'm going to show you, et cetera, et cetera. So it's like a huge team effort going behind this. So the very first paper that we put forward was like a couple months ago, which was already accepted, which is this beautiful JWST near-spec prism observations of WASP 39b. So you remember the previous transit spectrum that I showed you that had water? That was basically the thing that we have been seeing for years, always water, 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 because it's the only thing that we could track with our observations with HST. But now we were able to see this beautiful feature around 4.3, 4.4 microns of CO2. That was a new molecule for us to observe, right? That was not the only cool thing. The cool thing is that you can actually see the spectrum on the data itself. So I don't have to show you this transit depth as a function of wave. You can see it in the transit light curve itself. So I'm going to do a little bit of a game. So I want you to go back and forth between these two plots. So what's going to happen now is that this transit is going to happen as a function of wavelength. I'm going to start moving the pointer here. And you're going to see how the transit depth actually gets larger when we hit the CO2 band. Are you ready? Yeah? OK. 1, 2, 3, 4. I'm going to scream when I see the CO2 feature. Okay? So you can swap. So you see the baseline here is this dashed line. Now be careful. And now jump to this one. Now you see? By eye, you can see the transit depth. This is amazing. Like the fact that you can just go and watch it, like that's it. You have the detection there. Now, this is not only cool. I mean, it's very cool, of course. But CO2 is actually a very important molecule for constraining the metallicity of the planets. Here I'm showing 5 different metallicities in this paper by Safar Stamoklov, also a PhD student in Johns Hopkins. We're pointing here 5 different metallicities. From the lowest metallicity is like the dimmest color, and then to the highest metallicity is like the toughest color, like the one darker color. And you can see how detailed the CO2 feature is to metallicity. So if you change the metallicity a bit, then you dial the CO2 feature up and down, which is pretty amazing. So you can see by eye that the best fit is like, around like 1 to 0.5 dex metallicity, which is pretty cool just to see it by eye. This is not something you can follow, for instance, for water. Like, I love water features, and I love water in general because I like to drink it. But water, it's not that great for measuring metallicity, right? So here you have the water feature, here at this 3 micron mark. And you can see that with metallicity, it doesn't change that much. But CO2, that's a beautiful metallicimometer, I like to call it. So I'm putting it. So CO2 is an excellent metallicimometer. So we now have a new wavelength regime to follow metallicities to high precision with this CO2 feature, which is amazing. But this thing, it's only 1/5 of the story, because we had other 4 papers, or 5 papers actually, that we wanted to plot together. So these papers were released last week in the archive. 3 out of the 5 are in press. They're already accepted. There's 2 ones that are in review still. But what we did was to observe the transit spectrum of WASP-39b with different instruments. Here's NIRISS, there's NIRCam, here's NIRSpec with 1 mode, 395H, would give you like high resolution, which is, to us in space, that's like 3,000, which I know the high velocity folks are going to laugh at me, but that's fine. I can take it. And NIRSpec Prism, which covers all the way from 0.5 to 5 microns. So depending on what you want, if you want high resolution, then maybe you go to this mode. If you want only the optical part, and also relatively high resolution up to like 3 microns, then you go to NIRISS. If you want like a particular feature that you want to get at very high precision, then you go to NIRCam. So we were showcasing basically the different modes that you can use. You can choose your own story, right, with these instruments in JWST. There's one particular thing that I would like to highlight from these plots, which is an awesome feature that we spent at least like 3 weeks looking if it was real or not, which is one here that you see, the sulfur dioxide. It's a very tiny feature, but it's pretty obvious from the data. I have to be honest with you folks, when I saw that first, this is like a data reduction error. So I had to go back, and we all went back, and I was like convincing everyone like this is like an error, but it was not. It was like JWST works that well that you can see very tiny signatures. And sulfur dioxide is so important because this thing does not appear in equilibrium. If you have a gas, like a solar composition gas, and you let it go, you get to equilibrium, you don't see sulfur dioxide. This thing appears because there's some disequilibrium process happening in the atmosphere. And that process is photochemistry. So the best way that we could find to figure out that huge bump of sulfur dioxide was that UV photons basically hit some of these water molecules that, as you can see here, are pretty abundant. There's many water features around. They hit that and they just break it. And then that breaking actually produces like a chain reaction in which you form sulfur dioxide at the end. Doing those like photokinetic models actually gets you a pretty good constraint on how big that feature is, which was amazing. There was actually, I heard from Natalie Battaglia, the PI of this program, there was like a huge whiteboard with all the possible molecules that they were just hitting them one by one to all the chemists until they figured out it was like photochemistry, sulfur dioxide, which is pretty neat. This is not the only example of disequilibrium chemistry. We just put a paper. I don't have the time to go through this right now, but this is the new frontier, right? Chemistry beyond water and beyond equilibrium. There was also a paper today in the archive led by Wanwei Fu that we worked together on putting this for another exoplanet in which we also find signatures with JWST of disequilibrium chemistry, which probably for the planetary scientists in this room won't come as a surprise, right? Like, where do you expect equilibrium chemistry, right? Just your little box in your computer, basically. But this is amazing that we now have the precision to actually see it, which is great. So now, in this final 20 minutes, or like 10 minutes, because we want to leave some time for questions, for 15 minutes, I wanted to jump. Now, this is all that has been published so far, basically, to date. And today is like 4 months since the actual cycle 1 started for JWST. So it's pretty amazing that we're seeing all of this in just 4 months. But there's more. There's a future for JWST and for exoplanets that I wanted to share with you. This is, of course, a very biased view. First of all, because you're going to see it's focused a little bit on the work that I've been doing with all the folks. But also, it's biased because it's what interests me more. But since you folks invited me, I get the chance to talk about what I like, right? So I'm going to talk about what I think is going to be the future of JWST, but I'm pretty sure that we're going to be surprised by other stuff that I'm not going to talk about today. First point is that it's like a news flash. Exoplanets are 3D objects, right? I've been showing right now. I sold you the picture of transit spectroscopy as like a one-dimensional thing that the entire limb is like homogeneous. But I mean, look at their solar system planets. That's not real, right? Look at the Earth, like even. The entire terminator is not the same. You have different compositions slightly at the poles, at the different morning and evening limbs. If you have tested this, right? You've been outside in the morning and outside in the evening. It's totally different. So for exoplanets, that's also true, of course, I think, I suppose. So there's different techniques on how to do this, but I'm going to focus on one that is fairly new that we have been working on together on this. Because I'm going to take the advantage that you are now all transit spectroscopy experts. So the thing is that during transit spectroscopy, where we're trying to measure the starlight filtered through the atmosphere, right? And then you just see how much light you lose in this analysis. And then you build your transit spectrum, like the transit depth, that's a function of wavelength, which is the same thing that I've been showing you over and over during this talk. But what if the limb is not homogeneous, right? In particular, for highly radiated exoplanets, like the ones that I just showed you, again, they're like over 1,000 kelvins. It's pretty hard radiation there, right there that you have to focus on. For those planets, we do know by models, by general circulation models, that there should be like a jet of material going around. And that creates like a strong difference between, in particular, two sides of this limb. The one that we call the evening limb, I'm going to show here. The one that we call the evening limb, which goes from the day to night. So there's some material that flows in that direction. And there's also some material in the chemistry that it's exchanged between the night and the day that we call the morning limb. Of course, this morning and evening is like based on an Earth-centric way of living things, because these planets typically are tidally locked. So they have constant morning and constant evening. Such a boring place to live, right? In any case, so the thing is that if they're that different, then they might have different spectrum. And we, while measuring one transit spectrum, are averaging through those two. So my pitch here is like, wouldn't it be cool that you can actually extract the two, extract the two spectra out of this directly from the data? Such that you could extract like the evening spectrum and the morning spectrum and actually trace this chemistry difference between the two sides. Now, this thing that I just pitched you has been in the literature for a while. Like it has been in particular, Jonathan Forney explored this in 2010 with the first 3D models for hot Jupiters, right? They were already seeing that the evening and the mornings were different, as well as many other works. But one question that was in my mind that I couldn't sleep through while reading these papers was like, first of all, is how do you do this? How do you extract these two limbs out of the data? And the second one is like, does it really matter? Like, who cares? Like, if this is two and we take the average, like, okay, fine. But actually, it does matter. Because if they have like strikingly different chemistries in both sides, then you might be tricked with the average one. And you might say like, oh, this planet formed at this position, and it follows core accretion, and you live your happy life with that. But if they have different chemistries, then there's more to understand in order to build that intuition back to planet formation. So it's a dangerous game. So we teamed up together with the amazing Catherine Jones. Catherine Jones worked with me for a summer, but then we started working together for a year when I was in the max time. But then when I moved to Space Telescope 2, she's now a PhD student at the University of Bern. She's actually visiting in Baltimore. So like the worst host ever because I'm here for today. But I'm coming back, I swear. She was OK with that. So she said. So we actually wrote two papers on this. One in 2020 for the Journal of Open Source Software, building a software that we call Catwoman, the hero from the comics, which actually builds this two-sided model to actually fit it directly to light curves. And in a paper that we published last year, we actually went through the whole detail of creating a framework to actually extracting this from data. I won't go in detail about that because I don't have the time. But the main idea is that if you observe a transit light curve, and you have these asymmetric limbs, as we call them, you should be able to see the signature directly from the data. And this is a simulation from this paper from Espinoza and Jones last year. You should be actually able to see that. So if you could build this asymmetric model and fit it to your beautiful data that I just showed you, then maybe you can extract these two limbs. So I'm going to show you, this is unpublished work, that is work that we're doing right now. So I have a JWST cycle 1 proposal to exactly do this. The observation are sadly next year. But I figure like this should be, with the quality of data that we have, we should be able to do this right away. And in fact, we can do that like right now with the data that we have. So again, no tweeting and not photos and not anything, but I'm going to show you like the first measurement of these limb asymmetries now, which is pretty cool. I was super excited. I was like, OK. So here's the transit spectrum that I just showed you, right? This is for WST39, the last planet that I showed you, and the one that had like this beautiful water feature, the SO2 and the CO2, right? So what we did is that we went and fitted this 2-limb model, right? So what I'm going to show you here are the limb spectra, like the spectra of these two sites. And in red, I'm going to plot the evening limb, which will be like the hotter one. And the morning one, I'm going to plot in blue. So when I extracted these fits and I plotted them here, I could actually see from the evening limb, like this water feature, the same feature that you see here. We see it in the evening limb. And this bump here, this is the CO2 feature. We see it in the evening limb. But here's the surprise. If you go to the morning limb and you plot the spectrum here, you see that it's super flat. So they have different spectra. I mean, you can see that I see the same faces like, what does this mean, right? So I've been sitting on this. We're actually modeling together with a ton of folks from the ERS team. And one solution could be that maybe the morning is much cloudier than the evening, which actually is a prediction. Because the morning gets material from the night side, it should be much cooler. And some of the condensation from the night side could pass through the morning. Whereas from the evening, because you have all this radiation coming, it's very hard to condense stuff. So one solution could be that the morning it's cloudy and the evening it's not cloudy. So whenever you have cloudy spectra, all your features are muted. And this is exactly what you're seeing here. So we're exploring this in detail, like this fresh, like right off the press from like 2 weeks ago. But it's like we can do this, which is quite amazing. Like JWST data is just this good.
Point stuff seems to go very well through the lines.
Yeah, I mean, the retrievals that I built are fine. They're not perfect. Like the amplitude is not that correct. Also, one thing that I'm just starting bothering here, but one of the things that you see that point maybe go down, and then I've tracked the spectrum down here, and it keeps going down. So one thing that could be, it could be that there's like, we typically, when we model these things, we believe like, oh, there's gray clouds. Clouds is a gray opacity source. But we know in real life that's not the case, right? Like clouds are not gray observers. They have some modulation. And going down is like the classic feature of like mist scattering. So maybe that's what's going on. So I don't know. I won't put more into that, but this is pretty neat stuff that I'm very excited about. So exoplanet chemistry in 3D, which is pretty amazing, right? The fact that you can do this in 3D, it's quite interesting. Now, of course, some of you folks are wondering, like, okay, Néstor, you've been telling us all about giant planets. What about the small planets? Where are the aliens, right? Yeah. So I'm going to jump into rocky exoplanet science now, because this is something that you can actually do with JWST, which is pretty amazing. I'm going to put one example, which is the TRAPPIST-1 system. So if you haven't heard of this TRAPPIST-1 system, just Google TRAPPIST-1, and people are going nuts about this one. So TRAPPIST-1, it's a system that it's pretty nearby. Like actually, I don't remember. It's like 30 parsecs. So it's very close for astronomical standards. And it's a very weird system in many senses. First of all, the star, it's very tiny. It's like the star is the size of Jupiter, which is like, what? It's very cold, like around 2,000 kelvins. And the planets, it's not 1, 2, 3, it's 7 Earth-sized planets orbiting this very small star very nearby. This picture that you're seeing here, it's actually the cover of Nature when this system was discovered. And it's like one of the best covers I've ever seen on science publications. I love it so much. Because what you're seeing here, so we named these planets, TRAPPIST-1b, C, D, E, F, G, H. And you see something happening in this table. So for the planets that are very nearby the star, TRAPPIST-1b and TRAPPIST-1c, those ones are so hot that if they had atmospheres like the Earth, they probably would have evaporated all the water that they have in their atmospheres. So that's why you see some water vapor here. So they're like too hot to sustain liquid water in their surfaces, if we assume atmospheres more like the Earth, which is a big if. These other planets, D, E, and F, and maybe G too, you see some water in the table here. And those ones are like at the right distance, right? They're close enough that if they had like atmospheres like the Earth, then they could sustain this liquid water. They're in what we call the habitable zone, which is a nomenclature that I completely hate, but I'm just going to use it because, I mean, I don't have time to come up with a new one. And TRAPPIST-1H, you see some ice here. It's just too cold. So if you go there, just wear a jacket, right? That's the thing with TRAPPIST-1H. Now, Jupiter-sized planet, 3 in the habitable zone, or 4, depending on your limit. And there's about 200 hours of planned observations on JWST cycle 1. So there's a ton of interest, not only by the public, but by the astronomical community on really cracking this system. These are simulations, so TRAPPIST-1E. I'm bringing TRAPPIST-1E because I told you I'm going to bring the stuff that I like, and I like TRAPPIST-1E a lot. This is a program led by Nicole Lewis in a GTO program, and I'm the lead analyst for TRAPPIST-1E observations that are going to happen next year. This one is this one in the habitable zone. So I'm like super excited about this. We have 4 transits scheduled. And if we get lucky enough, we might get like a CO2 feature. Who knows? We're exploring that. But the main thing that we're trying to explore, and this is why I brought this plot, are these big CO2 features depending in your type of atmosphere. We have like Venus-like atmospheres or CO2-dominated atmospheres. The thing that peaks a lot is CO2. So that's the thing that we're hunting for first, at around 4.5 microns. There's also a little feature here at 3 microns. So without further ado, I'm going to show you some of the first transit spectra of TRAPPIST-1, because I have the privilege of being working on these teams. Not only the privilege, but there's a toll on me because I have to reduce data for them too. Of course, for these teams, not everything's free in life. So of course, I'm very happy to be working on these teams and doing this analysis with them. And there's in particular 2 planets that I'm going to be showing you the first observations of. Don't get too excited, there's no atmospheres. We're going to show some precisions that hopefully they will blow your mind as they blow mine. So the first one is TRAPPIST-1G. This is a program led by Olivia Lim from the University of Montreal. She got a program to observe like 7 or 8 transits of TRAPPIST-1 planets on some sort of reconnaissance. And what we're plotting here is, courtesy of Bjorn Benecke, what I'm plotting here is the JWST spectrum in black, and this is the HST spectrum. Like, look at those error bars. It's like 5 times better, which is amazing. The neat thing is that with HST, you were not able really to disentangle these models that I show here. And these are like the easiest models that you can disentangle, because those ones are assuming this planet has a hydrogen-dominated atmosphere, which is very unlikely. Right? Like this is bombarded by radiation. It's hard for small planets to like lock into hydrogen-dominated atmospheres. But with JWST data, you can already rule those out easily. And actually, you can rule out a ton of other possible atmospheres, like 100% dominated methane atmospheres, 100% dominated water atmospheres. Those are mostly also ruled out by this data, which is quite amazing. So the fact that you can get these precisions all the way, like you get those Spitzer error bars too. So we can get all the way to here with very nice precision. The dashed lines that you're seeing here, those are the scale heights of the planet. It's like 1, 2, and 3 scale heights of the planet, which is pretty amazing that we're almost there. And well, in the far infrared, above, like below 5 microns, above 2 microns, we are within 1 scale height of the precision, which is amazing. So that means that if you just crack more observations into this, you can actually start proving rocky exoplanet atmospheres, which is amazing. And then the other spectrum that I wanted to show you, which is a little bit of a cautionary tale on TRAPPIST-1 system, is this beautiful spectrum too. This is courtesy of myself. It's my own reduction. Of TRAPPIST-1C. We got just 1 observation out of the 4 that we need for this program to measure the CO2 feature. And again, you see like the HST error bars are like huge, but with JWST, just 1 observation of JWST, like you crack that down immediately, even for the Spitzer ones. But you see a little downturn here, like below 1.5 microns. Like there's something going on there. There's no way the atmosphere of the planet can do that. This has to be something else. And we think, I'm pretty convinced in particular, that this is stellar activity. So it so happens that transit spectroscopy, because it's a differential measurement, if you believe that your stellar photosphere is homogeneous, it works nicely. But if you have spots, even if you don't occult them, if you have spots in the stellar photosphere, that can introduce some signals in your transit spectrum. And we're pretty sure, I can show you some models if you want later, that Natalie Allen has been running. I'm pretty sure that that's very well fit by stellar contamination. We actually are so invested into this thing that I wanted to highlight a little bit too, the fact that we led with Ben Brackham study analysis group for NASA's Exoplanetary Exploration Program, just studying this problem. We got together people from the stellar physics community, the heliophysics community, and the planetary physics, exoplanetary physics community together. And like when I was going into this, leading this with Ben, we were like, okay, we're going to solve this. But then we went into it, and we came out with more questions that we had, which is pretty amazing because it means that there's a ton to do on this. So the jury is still not out on how to solve this. So several groups around the world, including ours at STSCI, trying to see how we can deal with this. We have very neat ideas, but we need actually to monitor, in this case for TRAPPIST-1, we need to monitor the star. That's like, you need to do that to actually crack the system up. If you want to learn more about what we wrote in this beautiful report, let's go. It's like under 100 pages. It has a very nice a high-level summary at the very first 2 pages if you only want to read about that. But this was a beautiful work by a ton of people that we're very, 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 very proud to have led with Ben. All right, but the new frontier that I wanted to showcase here is precision rocky atmospheric science. This is happening. It's happening very, very fast. In just, again, the first 4 months of observations, we're going to already get precisions down to the scale height of rocky exoplanets, which is like, it's mind-blowing. It's like the fact that we can do this. I was, to be very honest with you, like complete confidence, like I was very skeptical that this was going to be achieved in such a short amount of time. But JWST works so well, and it has better throughputs than we expected, that it just gives out this all beautiful science. All right, so summary of all that I've been talking today. First, we live in this golden era of exoplanetary atmospheric science. If you're excited about this, and you want to switch fields, now is the time. Beautiful data. Anyone can analyze it. I swear to God, JWST data is very easy to deal with. And we are putting out like IPython notebooks to deal with too, so it's even easier because there's tools out there to do that. JWST is currently observing the most precise spectra ever obtained of exoplanet atmospheres. And the science spans from gas to rocky exoplanets. And it's just, again, mind-blowing as I was just showing in this talk. And then finally, the future of exoplanet science is super bright. In only 4 months since the start of operations, JWST is already exploring a brand new frontiers on the field, including precision atmospheric chemistry and abundances, disequilibrium chemistry processes, including photochemistry, 3D chemical processes, and precision rocky exoplanet atmospheric science, and surface science. And if you want to know about that, ask me. I just didn't have the time to put it in the talk itself to give time for questions. If you want to ask me why, that's a free question that I leave there. That's it. I hope I got you excited about JWST science. Ready for questions.
All right, thanks, Nestor. Does anyone have, already, yes, many questions. I'll do this one since you're closer. Oh, sure. Should you want to yell that question?
You can scream and I can repeat it maybe, or, yeah.
Tell us about exoplanet surface science.
Exoplanet surface science, thank you, yes. Is my next extra slide. Yes, you can do rocky exoplanet surface with JWST. In particular, I have a program on this. So I'm like super biased. I have a program on this for cycle 1 that's happening next year. There's also a program by Lisa Dank, too, from the University of Montreal. For K2-141b, which is what we call a lava world. If you go to Google and do K2-141b, you're going to get a whole lot of weird things, including an alien picture. All of this is, of course, fake. Don't believe it. The real data we're going to obtain next year. And the beauty of this thing is that both Lisa and I are doing what we call a phase curve. We're actually following the orbit of the planet as it goes around the star. And depending on the surface properties, you're going to see different spectra. So here I'm showing, like at this phase, when the planet is facing a little bit to us, but mostly to the star, you see here 2 models, like the green, the very dark green, and the one, like the transparent one. Those are 2 different models for different surfaces. You don't see really the difference here, but as you start watching different phases of the planet, you start actually differentiating between those. And the different phases actually tell you, like actually can crack you down what kind of surface this planet has, which is absolutely amazing. So you can start doing that with JWST, and JWST only, at this level of precision. So this is the first exploration, but there's other lava worlds out there for which you can do this exciting science too. Thank you for that question.
over there. Hello.
That was a superb talk.
Thank you.
In addition to detecting the lava worlds, would it be possible to look at chemical interactions between atmospheres and lava surfaces due to drawdown effects?
Yes. Oh, this is an excellent question. I just spent 2 weeks ago in a beautiful conference in Greenberg Castle with some neat folks doing exoplanet science with JWST. Between them was Nick Cowan. He has worked on this so much because lava worlds are a whole mystery, because the question of do they have atmosphere is a huge question. These worlds are crazy that maybe in the daytime they're such irradiated, and then you have like this lava molten surface. This might outgas some sort of atmosphere, but there's basically no way that that surface spans the entire planet. So it has to disappear at some point. That creates two things. Winds that go like 4 to 5 times Mach. Like imagine that now you don't want to go there for vacation, like really. So that's like huge atmospheric winds going to the night side, and then the atmosphere disappears. So yes, all these sort of like questions, you can actually tell about these phase curves. I'm not plotting here, but we have some predictions on what if they have atmospheres in the day sides. And you could explore it with this data, yeah. It's pretty cool. Yep.
Thanks for a great talk.
Thank you.
I was wondering a little bit more about the photochemistry results. So the sulfur dioxide that indicated the photochemistry, where do we expect photochemistry to take place, and are there any other signatures that you would expect to see?
Yeah, that's a great question. So I think that the main observer right now that I have in my mind is SO2. This was actually predicted by Kevin Sandler like years ago. But we were just, like, we exoplanetarians, we were not paying, I mean, at least I was not paying that much attention to the literature in that end. But now everyone is going crazy by SO2. So now, I mean, I expect a flood of proposals in cycle 2 to go through that. But the excellent question that you make too on like what other molecules should go, there's some SO features actually in the UV part of the spectrum. So you can go back to HST in the UV part of the spectrum and explore that. Actually, Safar Rostamgalov, the PhD student that I mentioned, they work on the CO2 feature with NIRSPEC Prism. He has an accepted proposal for HST to observe like 4 transits of WST39 to go to the UV and try to check that feature out. So there's 2 sides of the story, and they're very complementary with each other. In terms of which planets you expect this, I think that's a great question on its own. We were not even sure we were going to observe that with WST39. So that's kind of an open question on its own. We're going to start exploring that in detail now. Yeah.
You mentioned the importance of stellar activity for interpreting transmission spectroscopy. Can you just say a bit about what JWST instrumentation can be used to characterize stellar activity?
Yes.
What other observations?
Oh, I'm super excited on this because we're planning proposals on this. One of the ideas that we have is that JWST can give you these one-shot spectra with NIRSPEC Prism in particular from 0.6 all the way to 5 microns. If you can get that as a time-resolved spectrum of TRAPPIST-1, for instance, you should be able to track down the different components of the atmosphere. Because, for example, the most recent works on TRAPPIST-1 believe that, and actually from the stellar contamination that we see, believe that the main component in the photosphere, it's actually faculae, like the bright spots in the surface. And these crazy temperatures, like 5,000 kelvins, which are like, what? So you could really tell that out if you had spectra from 0.6 to 5 microns, because bright spots like that, they emit a ton in the optical, but then they die off in the near infrared. If you have dark spots, on the other hand, it goes a little, it's just, the tail just keeps going. So if you get time-resolved spectra of TRAPPIST-1, you can actually track the different components out. And you don't even have to trust stellar models if you do that, because you can use the spectra itself from JWST to correct for that, or account for that in the transmission spectrum analysis. So Natalie Allen, for instance, is working a ton with me and other folks. We're working with Ben Rackham, with Julian David, a ton of folks around the world on trying to think of different ideas how to do this. But JWST has a lot to offer. Yes, definitely.
Yeah. It's pretty obvious when a molecule is present in the spectrum, like CO2 and water. The question really is one on quantitative spectroscopy. Namely, if you really want to measure the abundance of water or whatever, then you have a problem of there's the absorption line spectroscopy, absorption line produced in the planetary atmosphere. There's also absorption lines of the same element or molecule or different molecules that partially overlap. And you don't have spectral resolution to determine how much overlap there actually is. So I want to speculate a bit on how well one can do quantitative measurements. And in particular, if you want to measure the relative amount of water compared with CO2, then you have to somehow or another simulate or have a program to take into account these partial overlaps.
Yeah.
in the Earth's atmosphere.
Yeah, that's an excellent question. There's actually a whole team within an early release science team. It's just a team of like theory folks doing retrievals, trying to figure out stuff like this. So the overlap between molecules is real. It's something that you have to take into account. And there's a tricky business, especially with the smallest signatures one, because CO2, it's barely separated, and the water, there's a CO bump just at the edge of CO2 that you might think is like the CO bump is like really, really embedded into the CO2. So CO2 is very clear, but if you go to the smallest one, like the SiO2 feature that I showed, and there's other features that we're trying to figure out what they are, then that's a tricky business. That's a tricky business from the point of view of what molecules will you get out to actually measure that abundance, as you said, that these folks are studying. But there's other one, which I love the word that you use, which is quantitative spectroscopy. When do you claim a detection of a different molecule? How do you exactly do that? To me, right now, it's not exactly cut clear, especially at the very small signals, like SiO2, for instance. I think that one's pretty clear here, but there's other ones that we're trying to figure out. But the retrieval folks do this. They do this a lot. They try messing up with like the cross sections themselves. What if I have slightly wrong lines, right? And the bands just don't match what between different retrievals that they do. So this is definitely being studied. And I don't have a clear-cut question to you right now because it's a multi-dimensional problem. But yes, people are taking that into account. There's one thing that I wanted to mention, though, that sometimes the stellar lines themselves can also be tricky to disentangle from the atmospheric transit spectroscopy signals, because they can create like small dilution features. So if you have like a very broad band from the stellar spectrum, that can act as a dilution factor itself on the line that you're trying to extract. This is a very beautiful paper that Drake Deming wrote 2 years ago, and that's an effect that also we've been very careful to take into account. So yes, there's several intricacies in doing